Hey, in another video, I showed how you can take a design for a circuit board that you've made in something like Diptrace and submit it to a PCB fab like JLC PCB and just get a circuit board with all the parts soldered onto it in the mail. And that's a very particular process, and mostly what I was showing is how to go through the ordering process and selecting components from JLC. In this video, I'm just showing something more general, which is how to, from beginning to end, make a circuit board, from scratch, and then maybe I'll show how to use a different service for having the circuit boards manufactured and sent to you without having all of the parts assembled. You would just order the parts separately and solder them on yourself. So Diptrace is the software that I like to use at this point, but there are lots of other EDA softwares. That's the category of software. It's called EDA. And typically they all have the same process, which is that you create a schematic first, and then from that schematic drawing, you create a PCB layout. So Diptrace also has a couple other features that you should find in some form in any other EDA software, which is the ability to create components. So we're going to use components that are just built into Diptrace, and every piece of software will have libraries already in it. But and Diptrace also has the ability to search external sources, which is great. But a lot of people, and at some point, if you're doing this for any length of time, you will encounter situations where you want to make your own libraries of components, probably from scratch. So that may mean looking at the data sheet and creating the pattern or footprint from that. So that's looking at the measurement of the legs on the part or the pads that it gets soldered to on the board, and making sure that everything is exactly how it should be. Rather than trusting a symbol that someone else has made, and then or a component that someone else has made. And then the component in this case is kind of the collection or the pairing of the two parts, the pattern, which is the layout on the circuit board, and the schematic symbol. So from a pattern and a schematic symbol, you end up with a component, and you can have a library of your own parts. So that's a little bit more of an advanced topic. I think you can get pretty far just with the schematic tool and the PCB tool in whatever software you're using. So that's what we'll do. I've clicked schematic capture to create a new schematic, and we're going to create something from the Forrest Mims Engineer's Mini Notebook 555 timer circuits. Now, there are tons of Forrest Mims books. They're great. They all have schematics. They rarely have anything about actually producing it as a circuit board. So this is perfect. This is something that we want to make a board for, but we only have the schematic. So we're going to, instead of just creating a schematic from scratch, which is a different tutorial entirely, we're going to figure out how to translate this schematic to something in Diptrace. Like I said, you can do this in other software and it'll be similar. This is not a Diptrace tutorial necessarily, but I will go through the whole process and you'll see how it works in Diptrace. So the circuit we're going to make is a basic monostable circuit using a 555 timer. This is coming from Forrest Mims Engineer's Mini Notebook 555 timer and IC circuits. Let's see what the cover looks like. There are lots of these Forrest Mims books. They're all drawn by hand on these graph paper pages, and they were sold by Radio Shack back in the day. This is a simple circuit that basically uses the 555 timer chip. In our case, all these circuits that are in the book and most of his other books are just a schematic, and they don't have a circuit board layout. So this will be great. We'll be able to translate this to something in Diptrace and then turn it into a PCB layout. This circuit will take a pulse in on our board. It'll be a little button. You'll push the button, and that'll cause that signal to drop down to ground. And once that happens, a capacitor, C1 right here, will start charging up until it gets to a certain point, and then it will dump its voltage. And what that means is that the 555 will use that charging and discharging to create some event having to do with timing. And what that means is when I press this pulse for a moment, it actually will create a high output, or an output that's the same as the voltage in for a certain number of seconds. So for ours, we'll press a button just for a moment, and we'll get an LED to turn on for a second or 10 seconds or whatever we set it to. These are really cool. There are lots of discrete circuits like this, like where you can just basically make something without any code, without programming. There's no microcontroller involved. You could do this very easily with a microcontroller, but there's something really fun about building something like this. It's almost like building with Legos. If you want to change the timing, you just look at this chart or use a formula to find out what values you need to change. So in our case, if we use a 1 UF capacitor and a 10 mega ohm resistor, we'll end up with a 10-second output. So it's pretty cool. You can just switch out a part and change the timing. Okay, we'll actually use those values and see how that works. So let's start with the parts we need. We know we need a 555 timer. So there are a couple ways that you can make your way through the list here. One is that you can use the binoculars. I will say, if I search all libraries, it's not, this is one of the things that's not super great about Diptrace. It kind of takes a long time for it to filter the results, and there aren't a whole lot of options for filtering them. So using the binoculars is not the my go-to for finding something. It seems to get slower as it goes on too. So this is one place where I'm not excited about Diptrace, but otherwise I really like it. So I'm going to scroll through here because some of these don't look like they relate. And this one, NE555D, is the part that we want. You can see it has the same pins as that. But this is, because it has the D after it, I think this is surface mount. So let's choose P instead. And you can see here, now it has holes. So we're going to do everything through hole. That way we can just order the board and solder the parts on ourselves. So there's some others here, and they look to be the same. If you look at the schematic symbol and the pattern, they seem to look the same as the other one. One reason to choose a different one, though, is because the order of the pins here might be more convenient. So in this case, I think they all have pretty much the same arrangement, which frankly isn't ideal. For the circuit we're making, this is the ideal arrangement of the pins to make a neat drawing like this, but I don't know that we're going to find it. So let's just choose the through-hole version of this 555. And I can just drop it there, and that's that. Let me add some more components. I think if I look at the top here, I can find just general components. There's some capacitors. I know I need 2 of those. The 100 is basically about the width of the spacing between these parts. And you can see down on the bottom, it shows, or right here, the tooltip shows the actual dimensions. So you could use that to see how spread apart you want them to be, depending on which parts you're using. Now, the other thing I'd recommend doing is printing out this board that we make on a laser printer and just lining up the parts and making sure you've got everything right before you order anything. Okay, so we also need some resistors. I think this same general non-IPC category is going to have resistors. So let's just look here. Here's a couple resistors. I think we might need more than a couple, so I'll just drop them in there. There's also, I think, maybe under net ports, we have things like VCC, and which is the power coming in, and then also ground, which we might need a couple of. What other parts do we need? I think that's mostly it. So we also want a tactile switch. So let's see if it's just under the switches category here. Switches, tactile, this looks fine. A little bit of a clunky drawing here, but I think that'll be okay. Okay. Oh, and an LED. So let's look under here. I think it's under optical something. Opto emitters, LED. We don't want surface mount though. We want through hole. THT is short for through hole in this case. And that's it. Simple red 3mm or maybe 5mm LED. Okay. I'm hitting escape to get out of each tool that I enter into, but so there'll be a lot of hitting the escape key in what I'm doing, and I sometimes will forget to mention it. So let's see if we can basically go through each one of the pins here and make sure it's connected to the right thing. So let's first look at pin number 1, which seems to go to ground. And so what I'll do is just drag the ground symbol over here, and I will click on this place wire button and actually make a wire from the end of that connection down here. Now, if I hit escape and click on this wire, it shows me up here the net name. Now, the end game here for making a schematic drawing is not to lay this out as a drawing that humans can read, not only that, and one that has certain conventions to it that humans like. And one that looks understandable and neat and is maybe broken up on separate pages. Those are all human things. What we're really interested in is making a file that contains a list of how each of these things connects to each other. And those are called nets. So this is part of the same net, this ground symbol here and this pin on the chip. And so we could rename the net. Most of the nets I will leave alone and let it just create them as net 1, net 2, and so on. But ground is an important one that we'll come back to, and I think it's worth double-clicking and changing that name to ground. Okay, so I'm going to go on to pin number 2, which looks like it's the input. Now this is interesting because the input here just shows something coming in, but for us, we're actually going to make it this switch. So let's connect it using a wire again. And then I'm going to connect the other end to ground. Ground. No, it should be. Yeah, so we want it to connect to ground so that we can, anytime someone presses the button, it will go to ground, which is our pulse. If you look here, it's normally at VCC and then it drops to ground when someone pushes the button. So that's what we want. We do need a pull-up resistor here, and I've got one VCC here. Instead of having everything all come up to the same one like they do here, maybe I could add a second one. So I'll just Control-C, Control-V, and drag one over here. And I'm going to stick with the R1, C1, the numbers that are on the schematic to make it simple to look back and forth. So we've got R1 here. I think that's the only resistor. So what I'll do is I'll take R2 and I will make that my pull-up resistor for the switch. So if you've ever done anything with an Arduino, you know that when we have a switch like this, it's fine to, when you push the button, to have it go to ground, but what is it when you're not pushing the button? It's hard to say, it's just floating. So there's no place here where it's actually, there's nothing here to say that it's actually high when it's not being low, right? So we want to make sure that's has some connection when it's not going to ground. So what we're going to do is use a pull-up resistor, and I will put that right here. Now, you can see it's interesting how it bends like this because it doesn't want to just go straight down into this. That's not a good setup. So we're going to move it over a bit. And I think honestly I can get rid of this other VCC and just connect it up here. So here we go. I'm going to go at a right angle here, and I will also have a right angle up to here. Now notice I didn't go at it sideways. You want to go right into the port. It gets really clunky, especially in other software that I've used, if you connect them kind of from the side instead of right into it. So here's another thing. We don't know necessarily what this value is because there's nothing here, but I do know I want this to be 10K ohms. So I can actually put 10K here, but it doesn't show it. And that's because in Diptrace, I'd have to right click on it and choose its properties. I could do this with a bunch of parts at the same time, but just to show you under part markings, I can choose to show values. And there now it says it's 10K. So that's my pull-up resistor. So it's high unless I push the button, in which case it goes low. None of this is in the circuit here, but that's one of the only things that we'll have to kind of improvise. So pin 7, well, let's look at pin 8. I guess this, jumping around is not great, but I'll go back and review and make sure I got them all. But I'm trying to choose the easier ones first. So we know pin 8 goes to VCC. So I will just make this go right there. When you see a dot, that means they're actually connected. You can have lines go across others, and if there's no dot there, then they're not actually intersecting. Pin 7 goes through a resistor, R1, to pin 8. So I will take R1 over here and make sure that it does just that. Now, why didn't I make it go over somehow back to pin 8? It doesn't matter. It's all the same wire. And you can see when I hover over it, it turns blue and shows that's net 3. All of those parts are connected. All those wires are the same wire. Now, the other thing that pin 7 does is it goes to pin 6. So let's make that happen as well. Like I said, this is not a great arrangement for these pins, but it's not great to have a bunch of overlapping things. But I guess, just make this go over here, down to pin 7. Now that's weird that it did that jumping thing, but I'm going to leave it like that. That's a weird, I don't normally see that. Maybe I don't want to do that. So not seeing the dot there shows me that those aren't connected to each other. Okay, so pin 7 goes to pin 6. It also goes to R1. That one's all set. If this were on paper, I would literally be checking these off to make sure I didn't miss anything. Pin 6 goes to pin 7, which is already done, but it also goes to C1, which then goes to ground. So let's make that happen. So here's C1, and let's see, how can we do this neatly? Maybe let's just highlight all of this, and well, that didn't work. Let's move this down. Let's take C1 and we'll make pin 6 go there. It's not a good reason to cramp these all together because we've got plenty of space, so I should just kind of make a little more room. Okay. When I say we've got plenty of space, there's actually a page to this, so this is something that you could print out. There's pin 6 going to C1, and C1 is also going to ground. One thing that you'll see is, you know, like in here, it's good to have just like a line that goes straight through. So maybe I'll just move this over so it's lined up. And now we're at pin 5. Pin 5 goes through C2 to ground. Let's see if we can make that happen. I'm pressing the space bar to rotate these parts, and that's a very common thing to do. My hand is actually kind of hovering over the space bar. Okay, and you know, maybe I'll move this over so it's lined up. I think let's take a look and see where we are. We've got pin 1 going to ground. That looks right. We've got pin 2 going to our trigger, which has a pull-up resistor, and then the other side goes to ground. We've got pin 5, which is the control voltage pin that goes to a capacitor, which goes to ground. Move this guy over a little. And we've got pin 6 going both to C1 to ground and to pin 7. We've got pin 7 going through R1 to power, and pin 8 goes straight to power. Pin 4, we've not connected. That should also go to VCC. So I will just do this. And then the output, of course. So the output is going to be our LED. And what we can do is give it a resistor and have it go to ground out here. So if I connect this to this, one interesting thing is if I click that, you can see they all highlight and it shows it with its net name ground. So that's important to tie those all together. I don't want this to just be a random other net, but actually connected to ground. So let's make the last connections here, going from out to the LED and the LED to its current limiting resistor. Now we do have values for these. C1, we're going to use, for C1, we're going to use a 1 UF cap. And for C2, we're going to use 0.01. So it shows it there. That's basically to keep the 555 from freaking out sometimes. It's kind of an often you'll see pin 5 just tied to ground using a value like 0.01. Okay, I think we've got this resistor, R1. So we said we're going to use 10 mega ohms, and that will give us a 10-second output. There's a very simple formula for this, but we'll just go look at this graph. It's pretty easy. It's not exactly 10 seconds, but if we wanted the exact number, we can change this. We can use the formula, and we could change, you know, based on that instead of the chart. Capacitors generally are harder to find, you know, really specific numbers. So we probably want to keep 1 UF and then find a resistor that matches the formula if we were going to do that. R1 is going to be 10 mega ohms, so I will change that here. And we don't know what this would be necessarily because we don't know what the input voltage is at this point. So one thing I could do is just put our LED here, and that would be the value. It's fine. I'm going to highlight each of these parts that I just gave values to, and I'm going to make sure that their properties show the value part marking showing. Okay, there we go. That looks pretty good. This resistor we don't need, so I'm going to delete that. And I think that's pretty much it. Now, This is matching the schematic here. I added the LED for the output and the input is a button, but there is something else going on here. We've got VCC. Remember, these are from the category at the top that just says general. These things, what was it? No, it was from net ports. So these are just like kind of ports in the drawing. They don't equate to anything physical. In fact, if I click on it, you see there's no pattern here. So what we need is to actually have a place to connect power. So instead of, well, what we can do is just make like a little plug for it. And under connectors, we've got a ton of options. I think probably if we can just do a rectangular header that is 2.54 millimeters, meaning 0.1 inches, that's a pretty standard thing. And we don't want SMD, we want through hole. I'm just going to choose vertical receptacle. It's got it's 2.54 millimeters. Looks good to me. So this will become our power connector, and I'm just going to put it out here. And what I'll do is copy and paste the VCC and put it up here. And then I will copy and paste a ground, put it over here, and then I'll just make some wires to connect them. So this means that we have a separate plug for power and ground. This is something that in the schematic will often get left out, but when we actually draw it in software, we need to make sure it's there. I think that could be it. Okay, let's save this. I'm going to save as 555 monostable. Let's now just go to verification and do an electrical rule check. And it says there are no errors found. So if we were to have any errors in the schematic, we might see them here. An electrical rule check is what does that. If we go now to convert to PCB, we'll open the PCB side of the tool. We're just going to use the schematic rules, just hit OK. And here it is. So here's our board. It looks like a mess. And these blue wires are called rat lines or a rat's nest. And essentially, like, it doesn't make sense, right? Like, you can't have wires looking like this. So, well, you could. But, you know, one of the obvious questions is like, well, if we have to connect all of these and some of the lines cross, what do we do? Well, one thing is we can make a really simple board like this with just, you know, lines, wires, or traces or routes, as they're called, copper connections between them that don't go over each other. It's a very simple board, so we could do that. If it got really complicated, we can use both sides of the board. So when you order a circuit board, it would be really rare to order a one-sided board. It would be at least two sides. And when I say at least two sides, what does that mean? There could be four-sided boards or four-layer boards, as they're called, or 8-layer boards or more, 12-layer boards. What's actually happening is there are copper layers sandwiched inside the board. So that's much more complicated than we would do, but this could be, if it got too complicated to make all these connections, we could take advantage of the fact that we've got a front and a back of the board to make the connections we need. Like I said, this one's so simple, we probably can do it on one side. So I'm just orienting this. If I zoom in, I can see where the different parts are, I mean, the different nets are. The only one I named was ground, and you can see this little notch is actually a screen print on the board, and that's showing where the pin 1 is. And also the square pad is another telltale sign. So let's look at what these layers are. I can show all layers, and I can turn different layers on. So there's a good, if you search for all Eagle layers explained, Eagle is another EDA software, and there's a list of all the different layers that are in Eagle. They're essentially the same as the layers that are here, because our end game here is to not have a net list like we are with Schematic, but to have Gerber files. That's what we get out of this, is Gerber files. And those contain, each Gerber file has a different layer that it addresses. So the Silkscreen is here. You can see those are with green. So that's labels for the parts and also maybe an outline. There's a courtyard that says, you know, nothing else should be intruding into that space. Some of these are less useful to have on while we're working, so they're not showing up. And then there are a lot of things that are for the bottom layer of the board. All those are for the top layer of the board, and then they're repeated for the bottom layer. And then we've got the board cutout, which is actually the actual shape of the board that doesn't exist right now. So let's see. I'm curious what this gray layer is here. It must be top, okay, top terminals is actually where those, where the connections are from the part. Top assembly, there we go. So the board won't actually have these gray lines. It will have the green ones. They'll be printed in white, you know, by default, but it can be other colors. But top assembly shows us where the actual parts go, but those don't show up on the board itself. Okay, so what I'm going to do is make all the connections I need. It would probably be useful to still have this schematic available. Let's see. So let's kind of retrace what we were doing. We've got pin, so the numbering of the pins is 1, 2, and you can see them listed here, and even the function of them, 1, 2, 3, 4, 5, 6, 7, 8. Pin 1 we know is ground, and what I'm going to do is I'm going to ignore any ground connections. And actually I can right click and I can say hide net rat lines. And what that'll do is hide anything that's ground. And I'll explain why later. Everything ends up, I mean, a lot of these parts end up having a connection to ground, and it's good to just ignore them for now and then go back later and see how we can connect them. And if it's too hard to connect, there are some tricks to make that work. So we'll go with that. So let's look first. I think one of the easiest things is where's the LED? Okay, that's D1 because the LED is a diode. So that one is going to connect right to there. I'll just put it right off to the side here, and I will add its current limiting resistor over here. Again, I'm pressing space to flip these things as I go. This is the capacitor for pin 5. Here's the capacitor that actually deals with the timing. The other end of it goes to ground. That's why it's not showing anything here. And you can actually see it shows ground. This resistor is going to be connected between these two pins. So it looks crazy the way I'm doing it, but this can actually happen right between those two. So we can do that very easily. So let's, and we can actually put this one down here if we wanted to. Okay, it depends on the shape of our board and how we want it to look. But here's the pull-up resistor for the switch, and I will move this maybe like that. Here's our power connector, and I think that's all the parts. So let's try connecting them. So the way we do that is with this route manual button. I would not recommend doing auto routing, especially on a board like this. Auto routing to me is more for when you have like a crazy board that needs a million connections and it's just too hard to kind of work out yourself. But you know, for this kind of board, it's sort of fun to make the connections and kind of rearrange things that in a way that is maybe aesthetically pleasing and also is functional, right? We don't want to have the button too close to this because the wires are going to be coming off. It'd be hard to push the button. Maybe we want the LED in a specific place because there's going to be 3D printing of an enclosure, all those things. So let's start making some connections. So this we will connect here, and essentially a kind of just a kind of an accepted thing that we do is that we have these 45-degree angles everywhere. So this one's very convenient. We can do that. So you might have been asking like how we're going to make a connection from one side of the board to the other between pin 4 and pin 8. Because they both connect to power. So just going right under the chip is a really easy way to do that. Here's the LED. Here is one end of my current limiting resistor. This is another resistor. This one is going up here to the threshold. And these two are connected. This is connected and this is connected. I mean, that's a very easy board to lay out, right? So I can also just make this go around here and make this go here. So it's fine. You know, having right angles is generally frowned upon, but really it has to do with high-speed systems, high-speed circuits. There's nothing high-speed going on here. We can make these lines look like anything we want, really. But these are just conventions, having these 45-degree angles instead of right angles. And trying to have things flow in a natural way is like a good thing. But this looks like I've fulfilled all the requirements, honestly. I will next make the outline of the board. And I think maybe, well, just to show you that it's possible to make different shapes for boards, maybe what I'll do is go to Objects, Place Shape, and I'll just choose like oblong, which is kind of not really rectangular. Okay. Now, what it's done is, if I hit Escape and just click on that, you can see it's drawn it on the top assembly layer, and that's not what we're looking for. We actually want this to be the outline of the board. So we can change that right here to board cutout, and now that's the cutout of my board. That's it. Let's talk about, if I just go to verification and check design rules. What are the design rules? If I click on design rules here, it gives me a list of different rules, and honestly, sometimes you can just download these from the PCB manufacturer and it'll fill them in. But this is basically has to match up with the capabilities of the PCB fab. And we're going to use OSHPark to produce this board, and I can tell you these will all work fine. One thing that OSHPark recommends with Diptrace is to make sure that check copper pores is on. So all of those rules are what it goes by when we choose check design rules. And it says no errors found, which is quite odd because I haven't connected any of the grounds, but that's not what that's about. The design rules are about spacing and manufacturing capabilities. If I check net connectivity, it's going to find some problems because ground is broken in 6 different places, and it's showing me where they all are. So we'll fix that right now. One thing we could do is make those connections manually, and it wouldn't be a problem to do that. But the other thing we can do is create what's called a ground pour. So I'm going to click the ground pour or copper pour button here. And what I like to do is make it a very weird big size. On the last node here, I'll right click and hit enter. And what I'm going to do is I'm going to accept these options right now, except say that anything that actually isn't contiguous, isn't connected to the rest of the board is going to be removed automatically. And then under connectivity, I want to make sure that it represents the ground net. So what that means is it's going to pour copper in any available space on the board, and that is going to contribute to the ground net. So let's see what that does. Let's also add, well, let's stop here. We'll just say okay. So that didn't quite work. What happened? So let's go back and right click on the ground pour and choose properties. I think on the border section, we want it to be the size to be depending on the board, and I want it to snap to the board outline. So now what we should get, oh, what's happening? It's still not working. Well, I did some searching, well, not searching, but I just did some experimenting, and it's kind of interesting. I had to right click on this and choose, it was a shape. So I had to right click on it and choose convert to board outline. I don't remember having to do that before, but I don't usually make boards with a weird shape. So right clicking on that shape and choosing convert to board outline, even though it's already on the board cutout layer, that made a difference. So I, again, will make a weirdly shaped pour. I'll make sure it's going to remove anything unconnected, and I'm going to change the border to depend on the board size. And now it works. So basically what's happening is anywhere where there would be a ground connection, it should be making that connection, but you see the rat lines are still there. So let's click on that. If I go out here to the edges, well, if I click here, I should be able to go to properties and make sure that the connectivity is ground, and it's not. So let's try that again. Okay, so now the rat lines have disappeared. And if I again do a net connectivity check, we should see there are no errors now. Okay. But there's a potential for some other errors, like maybe the copper is too close to the board outline, or maybe some, like some components are now in the wrong place. So it's worth doing the design rules check, and there's no problem there either. Finally, I need to check and compare it to the schematic, which I called 555 monostable, and this will verify that there's nothing different between the two. Now, why would there be? Because, I created that schematic and based this board around it. Well, it's possible that we have to make changes back and forth. So for example, let's say I want a mounting hole here. Now we could add that here because there's actually a hardware section and we can use one of these. But what will happen is every time I make that comparison between the schematic and the board, it'll say they're different, sorry. So let's, in here, maybe add some mounting holes. It's a little weird to have mounting holes in the schematic, but not totally out of the question. So let's just see if under, is it the same thing, under hardware? Let's see where that is. Way on the bottom, objects, hardware, metric, 2.5 millimeter hole. I'm going to add this. And if I save and then go back over here, I can update this from the schematic. Choose the schematic and hit open. So now I've got this hole here that came from the schematic. So I'll drop it in here. And anytime I add something new and I've got this ground pour, I need to right click and update, because now you can see it's different. It's breaking the ground pour because this copper around this hole is not part of the ground net. So they have to be separated. One thing I could do is say, well, actually this should be added to a net, and I don't even have to choose it from a list. I can choose by the mouse pointer and say it should be part of that net. Now it didn't change the ground pour because, again, I'd have to right click and hit update. And now you can see there's no difference between that. One thing I might want to do, I've got all these ground connections, but those can be hard to solder by hand because there's a big pool of copper here. If we start removing some of the things here and only see the, wait, those are bottom. Let's, so what you can see at some point is that, yeah, this is what it would really look like, right? So it's just a hole with copper around it. And so what we need is maybe some way to separate the pad where we're going to solder the leg of the component from this big pool. And we can do that by right-clicking on the ground pour, hitting Properties, and under Connectivity, we can say there should be thermals. And like if I use 4-spoke 45 degrees and hit OK, you can see what it's doing now is it's making these little spokes. It's still electrically connected, but it's a lot easier to solder because the heat doesn't get sucked away by this big copper pad. So how do I get all the layers back really quick? Well, I'll just check them off. Okay, so this looks fine. Now, there are a couple things I don't, the Silkscreen doesn't look great. J1, S1 aren't necessarily useful, and R2, it would be nice if it showed me a value there. So let's do a few things. If I click on this, I can't necessarily move the label by itself, but I can click on it, hit F10, and that puts me in a different mode where I can move these around. Now, normally, if I right click on, say, this one and choose Properties, I can say don't show the ref des, which is the S1 there. So let's hide that. But for some reason, I can't do that on the mounting. On the mounting hole, I can't do that. So I can just move it off the board, and that's fine. But for these others, I probably do want to change that. Now, I think, again, like that's not useful. Having one that says U1 isn't that useful. And D1 probably isn't that useful either, but I'll leave it. I'll right click now that I've highlighted them using Control and hit Properties and tell it to hide the ref des for those. Now for these parts, I would like to have the values. So I'm going to click on all of those resistors and capacitors and right click. I messed that up. Click on all of them with Control and then right click and choose Properties. And I want the values to be shown. Okay, so now again, I'll have to use F10 to kind of get in this other mode where I can move things around. Now, I think one thing you could do is just say, well, as long as it's underneath the place where I'm going to solder, that's fine. It's okay to put Silkscreen over these gaps. It won't be noticeable on the finished thing. So, I think you could do that with the resistors, but then can I do that with the capacitor? It doesn't look like there's room. So I just have to decide what I want it to look like. And I think having the ref des and the value is handy. That looks fine. This one obviously is upside down, but I can just flip it without flipping the part. So this is R1 and this is R3, which is our LED. Okay, whatever. Looks okay to me. This is a 5mm LED. Just leave it alone. So I think this is, one other thing I would like to do is add a plus and minus here just to give people, like an idea of which one's which, even though they could look at it and figure it out. So I can go to Objects, Place Text, and I could add a plus sign and maybe also add a minus sign. And then, whoops, it always does this to me. Let me copy and paste, and I will change this one to a minus sign. Okay, now they are showing up on the top assembly layer, so that's not going to show up on the board. I want to highlight them both and change them to top silk. And now they're green, they will show up on the board. Okay, so I think that's probably okay for this demo. Anything else I want to show? Well, so far we've only looked at the top side of the board. And like I predicted, we were able to make all the connections without having to jump over to the other side of the board. But if we did need to, we could do that. Let's say this connection was going to be on the bottom side of the board. We can actually right click on it and change its layer. So trace layer bottom. So obviously we'd have to make the ground pour, and now you can see it just disappeared. Well, if I hit 1, I'm on the top side of the board. If I hit 2, I'm on the bottom side of the board. So you can see there's the connection on the bottom side of the board, and that's great. Now, the other thing is, it'd be great if we had the ground pour on the back of the board as well. So I'm going to the bottom side of the board, and I'm going to do the same thing. I'm just going to make this big old weird shaped ground pour. And I'm going to use the same settings. So depending on board, this should be connected to ground. And I think thermals, hit OK. And now this is what the bottom pour looks like. So now I should definitely do a design rule check. No problems. Definitely do a net connectivity check. No problems. And we can also compare it to the schematic just to make sure. Oh, pads don't match ground. Okay, pads don't coincide in net. Ground on schematic. Ground on line. I think it's just the mounting hole that's a difference. And that's because if we look at the schematic, it's not actually connected to ground. So that list, the only thing different in those two lists was the fact that this was not connected to ground. So what I can do is in here, I can copy and paste a ground and make sure that it's showing in the schematic, which is useful, that the mounting hole is actually connected to ground. So I'm saving this. And then over here, I am updating from the schematic. And now if I do a compare to schematic, there probably is not a problem anymore. Definitely shouldn't be because I just updated it. And then again, I'll just do design rule check. So it looks pretty good. So the last thing I'll do is I'll just save this. Probably should have saved it before. 555 monostable. Now, dip files are the circuit boards. DCH are the schematics. So I will just save it like this. And now to actually have this board produced, let's say by OSHPark, I would go to export, Gerber, and I could just say export all. I think the default settings are going to work fine. So I'll hit export all, include the Gerber and the drill files in this zip that we're going to make. It's called 555 monostable gerber.zip and hit OK. I will go over to my browser and I'm already at OSHPark and logged in here. I'm going to just choose browse for files. And I think I put it in downloads. It's going to go through those Gerber files and the drill files. It needs a drill file because all the holes there are a separate file. While it's processing, which, well, it only takes a second to process. But one thing I didn't mention, oh, this is interesting. It doesn't show the plus and minus here. So we'll have to figure out why that is. And I didn't mention that you can just put text or images or anything on the Silkscreen anywhere you want. So this looks okay, but let's try and figure out why. And I had this happen on another board that I happened to make recently. But the top, this should be on the top silk, and it is. Curious. So I'm not totally sure why those aren't showing up, but what I can do is change this to TrueType and choose my own font. Right now it's set to Tahoma, which, I don't know, looks okay. But that's interesting to know that you can add your own text using TrueType. So let me just add more. Place text here. I will just call this the LED stretcher. I'm not sure. Object, place text. I want to make sure this is placed on the bottom silk. So I'll just choose this here. And I will type LED stretcher again. Okay, Okay, yes, display. And you can see it flipped it around. One thing about the front and back of the board, even though I'm switching between top and bottom, the board is not flipping. So it's kind of like I'm looking through it with an X-ray vision. So obviously the text will be backwards in that case. So there we go. And I'd probably put maybe some version information or something. Another thing I'd like to do is add, when I remember, is to add a filled rectangle. And we could do that just right here. And maybe what I would do is be able to write, since this will be printed in white ink, I'd be able to write in marker something on there. And that's kind of useful. So let me save again and then export again. Gerber, export all, and choose the Gerbers and the drill files. I'll overwrite the one that was there. Yes, replace it. And there's no acknowledgement. It's done. So I just hit close. And then over at OSHPark, let's do the same thing. So I'll go back to the main page, browse for files, and try that again. So it's useful to know that maybe, hopefully, it's just the font choice. And like I said, I did produce a board recently and noticed that from a different manufacturer and noticed that that was missing. So it's interesting. It's missing again here, but it is there. It could be that the font doesn't include plus and minus. Not totally sure why that's not showing up. So I'm not going to sweat it right now. I think this is showing at least that we can have printing on the board. Shows that we can have a weird board shape. This is exactly what the board would look like. And when we hit continue, it actually shows us here's the top of the board, here's the bottom. There's where the drill marks will be, where the drill hits. The board outline is here. That's what the bottom layer and Silkscreen, they're all separated out into their separate layers. So this is interesting. It shows the MH1 there, but since it's outside the board cut out, it's not going to matter. And then this is the solder mask, which is when you look at a circuit board, obviously like there's some purple stuff, that's the solder mask. The less purple or lighter purple is where there's copper under the solder mask. And then there are parts of the board that have copper, or in this case, gold-plated copper, that is not does not have solder around it. So that's what the solder mask layer is in what they were showing. And also we can see it here if we go to layers and choose bottom mask, top mask, top mask. So if we just look at the top mask, this is showing where solder mask will not be applied. So that's it. Hopefully that shows you everything you need to know about how to make a circuit board, or at least how to translate a really simple schematic into a schematic in Diptrace, and then how to turn that into a circuit board, and then how to actually get it produced by OSHPark. Love these guys. This is like a really these are high quality boards. They look nice and they come pretty quickly. They're made in the US, which also means you're probably escaping a lot of tariff trouble right now. So that's it. Take care.